Hello, my name is Mario Lopez, and this is the third live for Physics 2212, the magnetic field of a bar magnet. So, introduction to this lab. The purpose of this lab is to measure magnetic field's dependence on distance, specifically with a bar magnet and a phone installed with the magnetometer app. This will be compared, the manual computations, with a computational model generated using the Biot-Savart law. So, a peek at our results here. The experimental dependence on distance between the magnet and the magnetometer is negative 2.7672. And the magnetic dipole moment is 3.496 am squared. And the computational model we derived is very closely resembles the data collected manually with only some minor deviations. So some fundamental physics properties to know, some concepts and such, is the Biot-Savart law, which is just the magnetic field, is equal to mu theta over 4 pi times 1 over r cubed times 3 times mu times r hat times mu dot product r hat times r hat minus mu. And the distance dependence formulas we're going to be using here is the magnitude of the bar magnet's magnetic field is equal to KRN, and the natural log of our x-axis magnetic field is lnk plus n times lnr. So the data collected here is pretty simple. We conducted 5 different trials right here and measured the distance and the total magnetic field of each of these trials. And all Excel did was just find the average distance and average magnetic field using the natural logs and such. And this is what the chart over here demonstrates. And after this, we performed the off-axis field trials, which is measuring the magnetic field at an off-axis of 45 degrees. And we have all of our data down here. So some observations. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x-axis. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So some calculations. Here we have our previous formulas for distance dependence. So using the line of best fit equation, n is equal to the slope, which is equal to negative 2.7672, which is how we derived our answer from the beginning. It's just the slope of the line of best fit. The magnetic dipole moment is a bit trickier to calculate. So first we calculate ln of k. This is the y-intercept at the line of best fit equation over here. And through this, we can use some algebraic manipulation to solve for k, and as well as this formula down here when compared to another magnetic field of a dipole formula, we can solve for mu, the magnetic dipole moment, which is 3.496 am squared. So here we have the code. Code is quite simple. First of all, just setting up our physical constants. Next up is creating the magnet at the origin right here, just the cylinder. And here we have the magnitude of the magnetic moment as previously calculated. Over here, we're just creating a function for the magnetic field itself, just the Biot-Savart law. And over here, we're creating some vectors to demonstrate each of the magnetic fields, both the perpendicular and on-axis ones. And yeah, this is just continuing just that. And over here, we have the off-axis one of 45 degrees. We're visualizing that one. Observation location. And the end of the code. And here's the final computational model. So the magnetic field of the perpendicular 3 over here, I believe it's this one right here, is this right here, figure 4. Our average magnetic field is 0.234335. So discussions, questions. What if we hadn't oriented our experiments to compensate for magnetic north and had instead laid out our meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So not accounting for Earth's magnetic field in the experiment would heavily augment the data. Instead of only looking at the magnetic field of the bar magnet, the magnetometer would have also been looking at the interaction between the bar magnet and Earth's magnetic field, causing the x value to not start at 0 and making this whole experiment, instead of just measuring the magnetic field of the bar magnet, we're measuring a net magnetic field between the Earth's magnetic field and the bar magnet itself. And what if we were to stick 2 identical magnets end to end and run the experiment again? How would this have caused our measurements to differ? So the 2 magnets stuck together would have combined to produce a more powerful magnetic field. It's possible the total magnetic field would have doubled. We just need to run some trials to prove this. And that's it. Hope the video satiates your curiosity, and thank you for watching. Please like and subscribe.